So guys, what we're going to do today is we are going to do the first of 2 days where we are going to fly over some very, very difficult concepts, and we're going to get the 30,000-foot view. Do you understand what that means? The idea, and it's actually a great country song, imagine if you're flying over the U.S. and you're just sort of looking out the window and you're just kind of getting a vague sense of what's down there, right? You're really not connecting with the people or the culture. You're just going, hey, look, there's farms. Guys, that's kind of what we're going to do today. Today, and actually this is even a slide in the notes that you don't need to write down. Today, guys, what we're going to do is we are going to take a very high pass over acids and bases. Understand that when we come back to this in March, good night. We're going to spend 5 to 6 weeks talking about acid-base chemistry, buffers, equilibrium. It's the hardest part of the year, chapters 16 and 17. But now what we're going to do is just soar over this high enough that at least you know enough about acids and bases that we can refer to them and you can go, oh yeah, acids give away hydrogen and bases take them in. Okay. Then guys, what we're going to do is on Monday, we are going to have a similarly superficial conversation about redox chemistry, just enough that you can say, oh yeah, oxidation means takes in electrons, reduction means gives away electrons, enough that we can at least talk about it superficially. Then guys, Wednesday, we're going to talk about dilution and titration, and then Friday of next week is going to be your first unit test. Yo. Okay, so guys, this is not new to you. A little bit of this will be, and let's talk about how this is going to be a little bit new. You ready? Let's review. Weak electrolytes, strong electrolytes, non-electrolytes. Think non-electrolytes first. What do non-electrolytes do? Dissolve in water. What don't they do? Break apart, right? That's why they don't conduct electricity, because they don't create charged particles. So those guys dissolve but don't ionize. Then we've got weak and strong electrolytes. What do strong electrolytes do? Dissolve and completely ionize. And then weak electrolytes, as that question that I think it was Spencer brought us to, weak electrolytes, guys, are in the middle. They partially break apart, and we end up with all 3 species, the non-ionized species, and then the ions that they create. You good? Okay, so guess what else does that? Acids and bases. So guys, what we are going to talk about today are weak acids, strong acids, weak bases, and strong bases. So what does a strong acid do? Completely breaks apart. What does a weak acid do? Partly breaks apart, right? And then conversely with bases, the same concepts hold. So guys, the only thing that's going to be new today is we are going to bring your understanding of weak and strong electrolytes to bear on acids and bases. Then what we're going to do is we're going to talk about the kinds of reactions that these acids and bases can have. One of them is review from last year. And then guys, the other ones are critical. The AP authors love to nitpick the solid base reactions and the gas forming reactions. And we're going to highlight those in a minute, and then we'll be done for the day. You ready to go? Here we go. So guys, talking about acids, no surprise, you already knew this. What makes an acid an acid? It gives away hydrogen ions. So when acids go into water, they give away hydrogen ions. But guys, let's see if you remember. What is the other term that we use for hydrogen ions? Protons. How's that work? What's the thought? All right, so a hydrogen atom is 1 proton, 0 neutrons, and 1 electron zipping around in space. That's a hydrogen atom. What happens if we make it a hydrogen ion with a +1 charge? How do we do that? Get rid of the electron. What's left? Get the idea? So guys, a hydrogen ion is a proton. So what do acids give away? Protons or hydrogen ions. They're the same thing. So with that said, these things then, of course, increase the concentration of hydrogen ions in water. Now, guys, you understand that this can happen strongly or this can happen weakly, right? Good heavens, how many acids do this to completion and give away all their protons? 7, and you memorized them, right? Some of you, yeah. But guys, that's the idea. When I had you memorize the 7 strong acids, now that word strong no longer in your brain means look out, it's going to hurt you. It will, but that's not what strong means. What does strong mean? Completely dissociates. So those 7 strong acids that you memorized are the acids that completely give away their protons. Now guys, think about this. Of those 7 strong acids, how many of them have more than 1 proton? HCl, HNO3, HI, HBr, HClO3, HClO4. They only have one, I'm sorry, too many fingers, that was 6. And H2SO4. Guys, this is a term that you need to understand, and it doesn't just apply to the strong acids, it applies to the weak acids as well. When we talk about acids, we qualify them by how many protons they give away. So, 6 of the 7 strong acids are what are called monoprotic. That means they release 1 hydrogen atom per molecule into solution. And again, HCl is an example, HI, HBr, HNO3, HClO3, HClO4, those are all the monoprotic strong acids. They're also monoprotic weak acids, but they all give away 1. So what about then the acids that have more than 1 proton to give away? What's the word for many? Poly. These are called the polyprotic acids. Guys, polyprotic acids have more than 1 hydrogen to give away. And please don't think it's just H2SO4. H2SO4 is the only polyprotic strong acid, but for example, H3PO4, which is what is called phosphoric acid. Guys, phosphoric acid is actually what is called a triprotic polyprotic acid. It's got 3. So there's a bunch of weak acids as well that give away more than 1 proton. Yeah. It's a good question, and actually that's where we're headed with this. What you're going to find out is that each successive protonation is weaker. So for example, if you think about H2SO4, let's use that as our example. Guys, H2SO4, and this is only relative to H2SO4. Guys, when we talk about sulfuric acid, only the first protonation is strong. Only the first protonation is complete. The second and we can even look at it, it looks like this. So this represents the first protonation. So H2SO4 releases a proton and it produces what is called bisulfate. Do you guys know that trick? Let me teach you the trick. SO4 is sulfate, right? What's the charge of sulfate? -2. If we add a hydrogen to it, notice that the charge goes down to -1, because what's the charge of the hydrogen? Positive. And guys, this is what is called bisulfate. Anytime you add a hydrogen to a polyatomic ion, add the prefix bi. So bicarbonate is carbonate, CO3, with a hydrogen, so it's HCO3, and that's bicarbonate from sodium bicarbonate, which is baking soda. Okay, so that's the trick. But anyway, so when we lose this proton, this is a proton, and then HSO4, but then guys, the trick is this. This HSO4 can then act as an acid. So what's that going to look like? what would the balanced equation look like for this thing releasing a proton? Well, guys, it would look like this. And actually, let me go up one. I didn't want to show you that last bullet yet. But guys, it looks like this. Bring the HSO4 down, make it the acid, and when it breaks apart, it releases another hydrogen, and then it forms sulfate. But guys, compare the first reaction with the second, and if you're paying attention, you're going to see something interesting about the way the first and second reactions are written. What's the difference? The double-headed arrow, right? What does this mean that this one's double-headed? Reaches equilibrium. This one is strong and goes to completion, and then guys, this will then further break down. You could even write it like this if you wanted, and just continue to string this together, and then this would make H and SO4 2-. So the idea is this completely breaks apart and this partially breaks apart. So now the $10,000 question is this. If you have a sulfuric acid solution, what's floating around in the solution? Let's do it by process of elimination. So guys, if you've battery acid, right, inside the battery of your car, sulfuric acid is in there. Is there any H2SO4 molecules in your battery? Why not? Where'd they go? They all broke apart. So guys, will we then have protons in solution? Absolutely. Bunches of them. Now, let's look at this. Will there be any bisulfate in solution? Well, it depends. What happens to the bisulfate? Well, let's come down here, and when we look down here, this is the life story of the bisulfate. Does the bisulfate break apart? All of it? Some of it. So we will have some of this left over, but as some of this breaks up, we'll also have some more protons, and then we'll also have some sulfate. So guys, in total then, what is in your battery? Is there any of this? No. Are there protons? Lots. Is there bisulfate? Yes. Is there more protons? Yes. Is there sulfate? Yes. The circled things are the things that you would have inside your battery. And that's actually listed for you here. You would have protons, sulfates, and bisulfates. You could just circle them if you'd like. Mm-hmm.
So the bisulfate, there's still some there because it's a weak electrolyte?
Correct. It's a weak electrolyte.
Is it possible to have something that would break down all the way?
The second step?
Yeah.
No, there's not. Because, and this is what Caleb and I were talking about, it's only, doesn't it say that? Yes. Only the first ionization can be complete, right? Because think about it this way. Think about it this way. You've memorized the strong acids, right? Is HSO4 a strong acid? No. Therefore, it can't completely ionize because it's not on our list of 7. So all successive ionizations will always be weaker. Is that okay? You guys ready for a little interesting tidbit though? If you have a hot tub, go grab your bottle of pH decreaser. Guess what it is? Sodium bisulfate. In order to drive the pH of your hot tub down, what you actually are doing is dumping sodium bisulfate salt into your hot tub. The sodium is a spectator. The bisulfate functions as a weak acid, and it drops protons and sulfate ions, which are harmless, into your hot tub, and it drops the pH by making it more acidic. What's that? Because you can't have bisulfate with it on its own. It will always be attached to something as a salt. Yeah. Groovy? Yeah.
pH is just,
No, so pH is the amount of hydrogen ion. But remember that it's an inverse scale because it's the negative log. So for example, and guys, let's do a pH review really quickly. The idea is this. If you have a pH of 1, okay, that means that the hydrogen ion concentration is 1 times 10 to the negative first, which is 0.1. Okay, that's molar. So the pH is this number. Okay, so if you have a pH of 7, the hydrogen ion concentration is 1 times 10 to the negative 7th, which is 0.1234561 molar. Okay. Then if you have a pH, let's go to the other end. If you have a pH of 14, the hydrogen ion concentration is 1 times 10 to the negative 14th, which is 1 molar. So the idea is the smaller the pH value, the stronger the acid, because the pH is the negative exponent in scientific notation of the concentration. Is that okay? So for now, all that you've got to really remember is that the smaller the number, the more acidic the solution. You guys all okay with that? Is that good? So remember 1 through 7 are the, 1 through 6 are the acids, 8 through 14 are the bases? Because the opposite of an acid is a base. Is that okay? And we'll get way more into this in March. You okay? All right, so let me clear this up. Was that enough? Is that okay? All right, yeah.
When does it come as is it hydronium? Is that when?
Yeah, so here, that's an interesting question, and I chose to, oh boy. Why did that go away? Okay, I'll just do this again. So you notice that like you notice that when I did, hold on, I've just got to quit out of this, it's confused. Oh, hold on. Yeah, just restart. Yeah. Yeah, I mean, that's what my son does on Halo, right? We've trained up a whole generation that if you ever get in trouble, just hit reset. Yeah, we're raising a generation of quitters. You laugh, but that's you guys. So guys, the idea is this. If you have a pH of 1, that means the hydrogen ion concentration is, I'll just write it like this, is 0.1, right? But McKay, you brought this up, wasn't it you? Here's the thing. What we're really talking about is hydronium ion concentration. The reason is this. These protons, and guys, you got to understand this. When an acid gives away hydrogen, where does the acid have to be in order to give away hydrogen? In water. And guys, those protons are not just floating around in water. These protons actually attack the water molecules and they form hydronium ion. So when we talk about acids, we talk about acids producing hydrogen ion, but all the time in the back of our head, we're actually understanding there is no free-floating hydrogen ions in an acid. They're all tied up in water as hydronium ion. But here's the thing. Because this always forms this, sometimes we'll talk about acids as containing hydrogen ions. Sometimes we'll talk about acids as containing hydronium ions, when in fact it really does contain hydronium ions, but sometimes it's just easier to think about it like this. So we'll use them interchangeably. Yeah. Yeah. Oh, absolutely. Yeah. Remember when we saw the video last time and they had the water and they were bubbling HCl through it? And as the HCl was going into the water, the light lit up? The reason is because those HCl molecules as a gas, when they go into the water, they break into hydrogen and chloride. The hydrogen attacks the water, forms hydronium, and it conducts. The chloride helps too, but that's the idea. Is that okay? You guys good? Okay, all right, so let's do this then, sort of as a little something for, drawing dots, for acids. This is all we just went through. So guys, let me offer this to you then as sort of a summary of, again, strong and weak acids and bases.
An acid is a substance that produces hydrogen ions when dissolved in water. Hydrogen chloride is an example of a common and important acid. When hydrogen chloride gas dissolves in water, it forms hydrochloric acid. Hydrogen chloride is very soluble in water and is completely dissociated. It is therefore a strong electrolyte.
Is that okay?
Nitric acid is another common strong acid.
You know what, guys, maybe we should say this. Notice the way that they're representing hydrochloric acid like that. What's wrong with the picture? If we're really dealing with what's in hydrochloric acid, what's wrong with the picture? This ain't it. Exactly. These hydrogens are not free floating. They're actually attached to the water in the form of hydronium.
Electrolyte. Nitric acid is another common strong acid. Upon dissolving in water, nitric acid completely ionizes to form an acidic solution.
Same deal, right? Hydrogens should be hydronium.
Like hydrogen chloride, nitric acid is a strong electrolyte. Acetic acid is the major ingredient of vinegar. When acetic acid is added to water, it does not completely ionize. It is therefore termed a weak electrolyte.
So now, guys, let's talk about this. Is acetic acid a strong acid? Of course, it says no. It tells you that it's weak. How do you know that it's not strong? You didn't memorize it. So this hydrogen comes off. But guys, will that hydrogen stay removed? Because this is a weak acid, all the while these molecules are releasing hydrogens, there are other acetate ions that are taking the hydrogens back. Now understand that there are billions and billions of molecules, so this proton is not probably going to go back to the same molecule that lost it, but these protons will be going back to the acetates. Just a second.
Or weak acid.
So they reconnect and they reach an equilibrium. Go ahead.
So when the hydrogen breaks off, it goes to a water molecule, right?
Absolutely, yes.
The acetic acid and the water molecule
Ionize.
fight over the...
That's exactly right. And so let's talk about this. This is really fascinating. Stop it right there. That's exactly what's happening, because this hydrogen ion is actually attached to water, right? But what happens is then when this acetate ion collides with the hydronium ion, we got the water over here, this acetate ion is actually able to strip the hydrogen away from the hydronium and back over here to form the unprotonated acid. So now apply that to this. Go back here to nitric acid, and this hydrogen is attached to water as hydronium ion. When these collide, nitrate can't do that. Nitrate does not have the ability to strip the hydrogen away from the hydronium, therefore it can't. So you guys ready for a deep thought? What makes a strong acid a strong acid? The answer is the ion that's left over when the strong acid releases the hydrogen can't steal the hydrogen back from hydronium. Think about that. Guys, the only thing that makes a strong acid is the fact that the negative ion that's left when the hydrogen goes away, that negative ion is too weak to go over here and strip the hydrogen back from hydronium. And there's only 7 molecules that cannot do that, and those make the 7 strong acids. You get the idea? Yeah. That's a good question. What is it about, hey guys, hold on. Don't miss this. What is it about those molecules or atoms, ions, chloride, bromide, iodide? What is it about those ions or atoms, or molecules that keep them from doing that? And the answer is full octets or stability. Cl negative, Br negative, and I negative all have complete octets that make them stable. And then the other ones, sulfate kind of, nitrate, ClO3 and ClO4 minus, are actually all what are called resonance stabilized molecules, and we're going to look more at that in about 3 months. There's something going on inside those ions that stabilize them and therefore keep them from being able to take the hydrogen back. We're going to get there soon, well, in 3 months. Yeah. Yeah. Exactly. So that acetate ion is not stable. Therefore, it can go and grab that hydrogen back to some extent. Yeah. Sort of neither. We've got a whole nother conversation to have. So again, guys, 30,000 feet, right? You got it. And I know that you want to get down and land the plane and walk around on the ground and talk about this. Guys, we're up at 30,000 feet, and you're going to have to be comfortable up there. So there are answers to your questions. We're just not going to go there today. So where are we going to go? Guys, now we're going to have a similar conversation about bases. And guys, the base conversation goes like this. What do acids do? Give away protons, hydrogen ions. What do bases do? Take them in, right. So bases are substances that accept protons. Now guys, you ready for a deep thought? In water, here's what they do. They increase the concentration of hydroxide ion. Now guys, there's one of two ways that this can happen. And we're going to go over them now. There's one of two ways that we can increase the concentration of hydroxide. What's the first one? Come with hydroxide, right? So the strong metal bases, the metal hydroxide bases, these guys dissociate in solution to release hydroxide. These are what we call the strong bases. And you've, you've memorized them. The group 1 and heavy group 2 hydroxides. How do the strong bases make the hydroxide ion concentration go up? They contain hydroxide. And when they dissolve in water, the hydroxide ion concentration goes up. Well, guys, it turns out there's another way to make the hydroxide ion concentration go up. And that's not by bringing hydroxide. These are what are called the non-hydroxide bases. The example that you need to know right now is ammonia, which is NH3. So guys, how does this work? How can NH3 make the hydroxide ion concentration go up in water? What does it do? It takes a hydrogen from water. And when you do, what's left? Hydroxide. So guys, when these things react with water, they do so by accepting protons. As a result, the water, when it loses the proton to NH3, you end up with NH4 plus and then hydroxide ion being left over. And guys, all of these are what are called the weak bases. So the strong bases contain hydroxide. The weak bases create hydroxide. Ooh, and this is a big mistake. Of course, you would have caught this. The weak bases, guys, create hydroxide by stealing a proton from water. But again, guys, because that is weak, that is an equilibrium process. You okay? Joey's hand's cramping up. You guys good? Yeah? Video time. Well, that's an awkward silence.
Ion in water. Bases are substances that increase the concentration of hydroxide ion in water. Water-soluble ionic hydroxides, such as sodium hydroxide, potassium hydroxide, and calcium hydroxide, are among the most common bases. When sodium hydroxide is dissolved in water, it completely dissociates into sodium and hydroxide ions. Because sodium hydroxide is completely ionized in solution, it is referred to as a strong base.
So guys, what's the silver guy with the positive charge? It's not a proton. What is it? Sodium, right? We dump sodium hydroxide into water. So the sodium ions are spectators. They just float around and do their thing. And then the hydroxide from the sodium hydroxide base increases the concentration of hydroxide. Does that jive? Okay, so let's try a weak base.
It is also, of course, a strong electrolyte. Ammonia does not contain the hydroxide ion, but is basic in water. When gaseous ammonia dissolves in water, it reacts with water to form...
Get it? Guys, so some questions for you. Ammonia is NH3. When NH3 goes into water, some of these NH3 molecules steal a hydrogen from water and form NH4. Of course, what's left over? Hydroxide, that makes it a base. Two questions for you. Question number one is this. What's going to happen when I hit play? They're going to bump back into each other, and what's going to take place? Proton's going to transfer back to the water, right? Again, their way of representing equilibrium. Yeah. That was my next question. So let me offer it as a question and then let's answer it. So guys, if you have a beaker or a spray bottle as a cleaner of ammonia solution, what is in the solution? What are the species that exist in solution? So let's think about it. Is there any NH3? Yes. Why? Why doesn't it all break apart? It's a weak base. Is there some NH4 plus? Is there some hydroxide? Yes. Now this is where we get into trouble. And again, guys, they're piloting these questions on the AP test even now. That was a question on the 14 test. The 2014 test was the first year where they implemented these things where you're actually drawing pictures on the test. And it wasn't ammonia, it was a different weak base. And they said, within this box, represent all the species that exist in solution, including their relative amounts. But say it was NH3. Well, you draw an NH3, you draw an NH4 plus, you draw a hydroxide. What else is in the beaker? Water. And they didn't mention it. So the question was, do you include the water? And then it was this big argument about, with a weak base, you have to include the water because the water is the species that becomes the hydroxide, and it became this big conversation. But guys, technically, yes, in this case, you would also include water. So there's the answer. It would be NH3, NH4 plus, hydroxide, and water. Yeah, that's a great, it's neat that you were thinking about that because that's where this is going. So guys, you can watch the rest of this, but you understand that this is going to transfer back, indicating equilibrium.
Ammonium and hydroxide.
Go ahead. You could go either way. The question would be, what else do you draw? So take HCl. If you were to draw HCl, oh no, I don't think they'd let you get away with this anymore. They're getting better about this. So originally they would have been down if you were doing HCl, just drawing protons and chlorides. But in fact, that's not what's in solution because the protons are attached to water as hydronium, and consequently you'd have to also include the waters, which explain where the hydronium came from. So
what if you were drawing as you draw hydronium, water, and chloride?
Correct, exactly, that's right, yeah. You guys are good, yeah.
What if there was no water?
There'd be no acid. Really.
So like what if like all the
Impossible. You can't saturate an acid. Yeah, no, what happens is the negative ion, we'll call it what it is, the conjugate base, will saturate before the protons will. So you can't push it that hard. You won't get there. Yeah. what happens to it is a spectator. Yeah, it's a spectator. Unless you were to add something like silver nitrate to it, and then the silver would precipitate the chloride. So the question is what are you doing with it? And they could do that. They could ask you, if you were to acidify a silver nitrate solution, what would you end up with? And you'd end up with silver chloride precipitate. But if you weren't doing anything to it and they just said draw a bucket of hydrochloric acid, the chloride's a spectator. It's not at all. No. Well, in order for it, here's the difference. You understand that chlorine is a gas, right? Chloride is not a gas. Chloride ion, Cl-, is not a gas, and it's stable. Because chlorine's got 7 valence electrons. When it picks up that additional 8th valence electron from the hydrogen, it stabilizes the ion in aqueous form and it doesn't turn into a gas. The only reason that chlorine is a gas is because if you've got 2 chlorine atoms, they're so electron hungry they'll share with each other, and then you end up with that single covalent bond forming Cl2. Remember, it's diatomic, and it's that Cl2 molecule that is not polar and therefore a gas. But chloride ion is stabilized without another chlorine, and it is polar and therefore stays in the water rather than being given off as a gas. Yeah, go ahead.
So on the AP test, did they ever ask you to draw HCl? And well, they wouldn't ask that time.
Yeah.
Ask that to tell you not to draw, but the way you draw the spectator ions are not to draw the spectator.
No, so 2 thoughts. When you're drawing, and again, we're still feeling this out, right? One of the hardest things about being an AP teacher is trying to predict what they're looking for on the test. I go to conferences all year long to try to rub up against the people that write the questions so I can get a sense of that. What we're seeing is when you're drawing pictures, they want you to represent everything. When you're writing balanced equations, it will always be a net ionic equation without the spectators. Yeah, it's a good question. So the question, it could be 2 different things. The net ionic equation for HCl could be this. Could be that. Or it could be this. But in either case, the chloride is not a spectator. The reason the chloride is not a spectator is because it doesn't start as an ion. It actually is releasing an electron and therefore it's doing chemistry. Okay? You guys good? All right. So guys, strong acids, bases, weak acids, bases, y'all groovy? Groovy. All right. So now guys, we need to talk about their relative strengths. This is review and we're going to treat it as such. So the idea is this, and we've already touched on it. What do strong acids and bases do? Completely dissociate into ions, right? And then weak acids and bases reach equilibrium. I'll wait for you to write it down if you need. Okay, so guys, with that said, well, you're still writing. What we're going to do for the remainder of the day today is we are going to talk about the 3 types of acid-base reactions that you need to know. Neutralization reactions, solid-base reactions, and then gas-forming reactions. And guys, here's the deal. You need to plant mental flags in your brain. I mean, if you sort of picture the Israelites wandering through the desert and they used to stack up these little piles of rocks to remind them where they've come from, because you need to do the same thing in your brain. You need to build little mental piles of rocks that tell you, this is somewhere I've been and I need to be able to get back here. Because the AP authors expect that you have memorized these specific reactions. They will unapologetically put these on the test and expect you to be able to intelligently regurgitate them. So you might put, I don't know what you need to do, but these are important. So here we go. These are the reactions that you need to know. First of all, neutralization reactions. So when you have an acid and a metal hydroxide base, guys, what are the metal hydroxide bases? Which ones are those? Strong bases, right? When you have an acid and a strong base reacting together, they always form salt and water. Now, guys, that doesn't mean NaCl, right? We understand as chemists that salt is way more than table salt. So what are salts? What is a salt? It's a positive ion, which is a metal, and a negative ion, which is either a nonmetal or a polyatomic, bonded together. So guys, salts are ionic substances where you have a positive and a negative ion. Now guys, just a second. So what you need to now understand is that the cation in a salt always comes from the base, and the anion from the salt always comes from an acid. We're going to talk way more about this in March when we talk about the acidic properties of salt solutions. But for now, you've just got to understand this, and I'll explain it to you better in a second. Yeah?
Does acid have to be strong?
It does not. And here's the thing that's interesting, and we're going to talk more about this in April or March, but you've got 4 different combinations, right? Strong acid, strong base, weak acid, weak base, and then strong, weak, strong, weak. The deal is this. Anytime you have a strong component, it can force the weak thing to completely dissociate. Yeah, so anytime there's a strong something, even if the other dude's a weak something, it will go to completion because the strong something forces it to. So guys, let me show you an example of what we're talking about here on the board. HCl. Strong acid? Yeah. KOH, strong base? Yeah. What are they going to form when they react together? Well, guys, this will be a double displacement reaction. Who does the H hook up with? Maybe we should write in charges in case you're not comfortable. So guys, the H is positive, the Cl is negative, the K is positive, the OH is negative. Who does the H hook up with? The OH, what's it make? Water. What does the Cl hook up with? The K. What does that make? Please don't write down CLK. KCl. So guys, the idea is this. Your products are KCl and water. Now guys, watch. Where did the K come from? The base. Where did the Cl come from? The acid. That's what this means. The cation always comes from the base, and the anion always comes from the acid. So guys, any salt can actually be traced back to an acid and base parent. So if you've got sodium sulfate, well, let's do something a little easier than that. If you've got what about sodium fluoride? They put it in your toothpaste, right? Where does sodium fluoride come from? Well, sodium hydroxide is the base and hydrofluoric acid is the acid. Any salt can be tracked back to an acid-base reaction. Get the idea? Okay, so that's the first one you need to know, neutralization reactions. Because the next one that you need to know, and we just did this, the next one that you need to know are reactions involving solid reactants. You ready? This is deep. Write it down. This could blow your mind. You ready? Just because a substance is not a strong base doesn't mean it's not a good base. Guys, some of the most effective bases that we know of are not strong bases. What? some of the most effective bases that we know of are not strong bases. A wonderful example of this is aluminum hydroxide. Guys, aluminum hydroxide is the active ingredient in Tums and Rolaids and other antacids. So your tummy is a big old bag of hydrochloric acid, and if you've got too much acid inside there, you want to neutralize some of that acid. So if you've got too much acid, what do you need to add? A base. And you'd like it to be a really effective base so that your antacid tablet's not as big as your head, right? So if you need an effective base, guys, a very, very effective base is aluminum hydroxide. That's what's in Tums and Rolaids. Why would aluminum hydroxide, given what you see on the board in blue, be a really good base? It's got 3 hydroxides. We call that tribasic. Guys, this is a really good base. Aluminum hydroxide is very effective as a base, but it's not a strong base. Why is it not a strong base? It doesn't dissolve in water. But guys, remember, you are now a chemist. You are not some dude strolling down the street that's ignorant to what we're discussing. Guys, in the general population, strong means strong. To a chemist, strong means dissolves in water completely. So guys, you can be a kick-ass base and not be strong, right? And aluminum hydroxide is a wonderful example. This is a really good base. It's just not a strong base because it doesn't dissolve in water. So when you take your Tums tablet, why is that a Tums tablet and not Tums liquid? Doesn't dissolve in water. But they do have liquid antacids, right? But what do you have to do to them first? Shake them up, because the base actually doesn't dissolve in water, so you got to shake them up to get all the base gook off the bottom so you can then swill it back. So guys, these really good bases are not strong bases because they don't dissolve in water. Yeah? Are you okay? Do you get the idea? So guys, what does the chemistry look like then? Well, gang, it radically changes the net ionic equation. So please do this. Magnesium hydroxide. This is the stuff in milk of magnesia. That stuff is nasty. Have you ever had to take milk of magnesia? It's one of those things your mom gives you because she's just so sick of you being sick that she just wants to get back at you. Guys, seriously, it is nasty. So guys, magnesium hydroxide is a really good base. It's what we call dibasic. But is magnesium hydroxide a strong base? No, look at where it is. It is not a heavy group 2 metal. It's calcium down that forms the strong bases. Magnesium hydroxide don't dissolve in water, but it's still a really good base. So guys, do this. Draw the net ionic equation for this, or not draw, write. Write the net ionic equation for this reaction. This is what goes on inside your tummy when you take milk of magnesia. Whole thing. Whole thing. You can't separate one from the other or there wouldn't be a reaction. I'll give you another minute. You guys okay? So let's take a look at it. And I'd like to try to sort of leverage your idea, but let's see if we can do it. So guys, here's what we've got. We've got MgOH. Oh boy. Let's see if I can go slower. It may just, yeah. MgOH2 plus HCl. So now guys, let's talk about products. What is this going to form? Water and MgCl2. That is our salt. So we need a 2 there, and I believe that balances. We okay? Oh, we do. Thank you. You're right. Okay. All right, so now, guys, let's see how we do. No, you know what? I'm not going to try your shortcut. I'm going to write this out. So MgOH2, we are now going to do a complete ionic equation. MgOH2, how do we represent that in water? Does it dissolve? No. So that doesn't change. MgOH2, and guys, forgive me, there's nothing I can do about my pen, doesn't dissolve in water, therefore we can't represent it as magnesium ions and hydroxide ions. Now what about HCl? Does it dissolve, does it ionize in water? Sure. So 2 protons and 2 chlorides. Now what about water? Does water ionize in water? No. And then what about MgCl2? Does it ionize in water? Is it soluble? All halogens are soluble unless it's bonded to silver, lead, or mercury, and that's not this. So this would be Mg2 plus and 2 chlorides minus. Seriously? Okay. Like so. Now, guys, what we need to do is we need to kill our spectators. Magnesium starts as a solid salt and ends up as an ion. Did it do chemistry? Yes. Hydroxide starts as an ion in a salt and ends up tied up in water. Did it do chemistry? Yeah. Hydrogen ion starts as an ion and ends up tied up in water. Did it do chemistry? Yeah. Chloride starts as an ion in solution and ends up as an ion solution. Did it do chemistry? That's your only spectator. What's left is your net ionic equation. Good? Okay. Because we've got 2 more reactions to go. It's interesting how this is really struggling. Okay, last thing we need to talk about are what are called the gas-forming reactions. Guys, these are the reactions that made science fair so much fun when you all made the little volcano thing, right? The vinegar and the baking soda. Vinegar is an acid, acetic acid. Baking soda is a base, sodium bicarbonate. You put them together, it makes a gas. And bubbles and red food coloring and volcanoes. Well, guys, you need to know 2 types of acid reactions that form gases. The first one are reactions that involve the sulfides. Not sulfates and not sulfites, the sulfides. So, hoping against hope, let's see if I can write. Try this on for size. HCl, yeah, that's better, and sodium sulfide. If you take a chunk of sodium sulfide, or even a sodium sulfide solution, let's say it's a solution, doesn't matter. It's a salt that dissolves in water. And if we react these together, what do they make? Double displacement reaction, right? What are they going to make? The H will hook up with the sulfide, and that makes H, oh, there we go, now it's screwed up again, H2S, and then our salt is NaCl, and we need a 2 there and a 2 there. Now, guys, what does this look like as a complete ionic equation? Well, HCl is a strong electrolyte, so it's 2H plus. Chloride is a strong electrolyte, so it's 2Cl minus. Na2S, by the way, is soluble in water, so that's 2Na plus, and then sulfide 2 minus. Now, what about H2S? Does it dissolve in water?
The answer
is no.
How do
you know that?
Because
you've been to Yellowstone and you've smelled that horrible, nasty, rotten egg smell.
Or maybe you haven't been there.
But guys, hydrogen sulfide gas is the gas that we think of as being rotten egg smell.
It is a
gas.
It doesn't dissolve in water as it bubbles out.
So this
doesn't
change,
and then our other product is NaCl. And I pray that if you know nothing else, you know that table salt dissolves in water. What on earth?
Apparently not. Okay, so now guys, let's check our spectators. Do protons do chemistry? Yeah, because they go away as a gas. Does chloride do chemistry? No chemistry. Does sodium ion do chemistry? No chemistry. Does sulfide ion do chemistry? It does. There's your net ionic equation. Now guys, keeping with the theme, I've got to quit out of this again. And we've got one more to go. And then we're done. So guys, when will you see gases form with acids? 1, when you have sulfides. 2, when you have carbonates and bicarbonates. And guys, it doesn't matter if it's a carbonate or a bicarbonate. The only difference is the way the equation balances. So let's do carbonate. You ready? This is interesting. So let's do HCl and let's react that with not baking soda. Let's do sodium carbonate. If it was bicarbonate, that would be baking soda. So guys, what is this going to form? Write down the products. You got it? So the H is going to hook up with the carbonate. But carbonate, as you know, because you know the polyatomics, carbonate's -2. Oh, this should be Na2CO3. Thank you. So guys, carbonate is -2. So one of your products will be H2CO3. Your other product will be Na, good heavens, Cl, and we need a 2 there, and we need a 2 there. But guys, here's the thing that's cool. That's not the end of the story. This, it's actually called carbonic acid. This carbonic acid is not stable. So what happens then is this carbonic acid actually further breaks down into carbon dioxide and water. So it turns out, guys, that all of the carbonic acid that is formed by this reaction actually gets released as carbon dioxide and water. So what you actually end up with as your products are these. You get table salt, carbon dioxide, and water. So what are your spectators? Let's see if we can do this without writing down the complete ionic equation. So with the understanding that this is in the presence of water, does hydrogen do chemistry? Starts out as an ion, ends up tied up in water. So hydrogen does chemistry. Does chloride do chemistry? Does it start dissolved in water? Yeah. Does sodium chloride dissolve in water? Yeah. So chloride is a spectator. It doesn't do any chemistry. Does sodium ion do chemistry? It starts dissolved in water. Sodium carbonate dissolves in water. It starts dissolved in water. It ends up dissolved in water.
Sophomore, this is Mr. Larson inviting you to our...
So guys, sodium ion does not do any chemistry. What about the carbonate? Does carbonate do chemistry? It starts out dissolved in water. It doesn't end up there. And so it does chemistry. And then what's left over? Carbon dioxide and water. So this is the net ionic equation for any time you add an acid to a carbonate. And then a bicarbonate's a little bit different because a bicarbonate would actually have a hydrogen there and its charge would be 1- rather than 2-. Okay? So again, guys, you've got to get really familiar with those. Anytime you see a reaction with an acid and a sulfide, your brain should go, boom, that's going to make a gas. Anytime you have an acid with a carbonate, that's going to make a gas. Anytime you have an acid with a bicarbonate, that's going to make a gas. You good? All right. Guys, here, I'm just going to quit for good. Here, guys, is your homework. Don't forget to turn chapter 4 into the basket. And I think so long as they did the announcements, we're certainly free to go. So guys, let's do chapter 4 in the basket. And just excuse yourselves when you're done. I'm going to stop recording.